Yeah, so again, hello, and thank you for coming for the second day of our bootcamp. Hopefully, you are alive from the previous day. And if you have any questions about previous day, maybe it's better to ask them now. If not, we'll continue with the new stuff. But first, let me remind you some stuff from yesterday. So the first thing is the training scheme. Yeah, so we are iterating over the range of total iterations. And each iteration consists of three simple steps. Obtaining data, then doing a forward step where we run our model on this data and calculate outputs. And then we do backward step where we update our model given model and loss. But we didn't actually discuss what is a model apart from being some computational graph. So yeah, model, we said it's a computational graph, meaning that it's some way of going from input data to output through some intermediate layers where each layer is just some function, like any almost function that takes either input data as input or input data and output of previous layers or just output of some previous layers. Yeah, like this. So we have input data, we have our layer, and our layer returns some output. And it has as input either this or this. So what do we mean by layer is some function? We say that it can be any function, but with a mark that it ideally should be differentiable, or we should be able to come up with some tricks at non-differentiable points. For example, we can just like bypass the gradient and it will work for some layers. For some layers, it won't work, and then we should maybe come up with some other trick or avoid using such sort of layer. So you can define layer as you wish. Maybe you want to define layer as 2 multiplied by sinus x, like here. Or maybe you want to split this into 2 layers. So like one layer is taking sinus, another layer is multiplying by 2. It's up to you. And PyTorch inside do something like this. Yeah, so it splits on simple operations that it knows how to handle well. So yeah, we can define layers. They can be either some simple layers or maybe some more complicated layers, but we have some traditional or standard layers that are commonly used in deep learning theory. So these are fully connected layers, convolutional layers, and pooling layers that we'll cover today. However, some neural networks, they are so commonly used that you can use the whole neural network as just one layer of your larger deep neural network. For example, there are recurrent neural networks that we'll cover tomorrow, and you can use the recurrent neural network as just one layer inside your bigger deep neural network, or transformer for which we'll cover on Thursday. So let's start with fully connected layers. This is the simplest type of layers, and it's basically some matrix vector multiplication or a weighted sum of inputs. So let's say we have an input, and this is some vector, let's say in R4, meaning that there are only 4 elements. And our parameters for our network are some weights which we use for weighted sum, meaning that we take this element, multiply it with some weight, with some coefficient, then we add this element multiplied by some coefficient, then this element multiplied by some another coefficient, and this element multiplied by some other coefficient. And this all results in a single weighted sum element here. Then for the second element, we do exactly the same thing, but we may use different weights. And then we have this one also with different weights, etc. So the result of one fully connected layer is a weighted sum of all elements from a previous layer. And yeah. Oh, I'll show you an example in a mess in the next slide. So the picture which we saw before is equivalent to this sort of structure where we have input like vector, then we have a hidden layer like one weighted sum, then we had output layer, another output sum, and our output is just the output of this output layer, meaning that this is our hidden layer, this is our output layer, this is our output. We have just two vector of size 2 as our output. And the last layer sometimes is called like final layer or output layer, and all other layers are called hidden layers. Input, which is just your data, sometimes is also called input layer, and people sometimes also like count it when counting how many layers you have. Yeah. So if your network consists only of these fully connected layers, your network is called multi-layer perceptron. And why so? Actually, so this whole view of how you look at multi-layer perceptron and fully connected layers is a bit inspired by biology. You can say that all these circles here are like nodes, which are like neurons in your brain, and your neurons are communicating with other neurons in some way, which you define as this arrow here. And you say this arrow has some sort of weight, measuring how like important this neuron is for this neuron. And when you have multiple of those, you have something which reminds you of a brain structure. And that's also why like all neural networks started from this layer, and that's probably why they're called neural networks. And this multiplication of each element is the result of a function that we were talking before, right? We'll see what how this multiplication works in the second slide, in the next slide. So, yeah, there is one thing regarding literature which probably is a bit confusing, is how to count layers in a multi-layer perceptron. For example, here, most literature probably says that this is a 3-layer MLP, because you have like input layer, you have one hidden layer and one output layer. However, others will say there are only 2 layers, because there are only like one set of arrows and a second set of errors. So it's up to you. Just be consistent, and maybe it's better to write like we have 2 fully connected layers. It would be clearer than saying 3-layer MLP. Yeah, this is example of a 5-layer one. Yeah, so I explained you visually, but probably it was a bit confusing. So let's look at it mathematically. Maybe it will be clearer. So your fully connected layer looks like this. You have your vector x, some weights which you define as the matrix W, and bias B, just like another vector. And then we calculate matrix vector multiplication Wx plus B, so something which is linear, like linear transform. And then we apply some activation function, also known as nonlinearity. What is nonlinearity? Nonlinearity is any element-wise function that you apply on your vector. For example, it can be sign. Let's say that if your element is greater than 0, you change it to 1. If it's smaller than 0, you change it to 0 or to -1, let's say. We'll look at types of activation functions on the next slide. But why do we need nonlinearity? Imagine we do not have this sigma here, we only have Wx plus b. And let's say we have something like this, where we have one matrix W here and another matrix W here. Let's say W1 and W2. And so in the first layer, we'll calculate W1x plus B1. And then on the second layer, we'll multiply this by W2 and add B2. If we open the brackets, we'll notice that this is actually something like this, which can be rewritten like W3x plus B3. Meaning that instead of having two layers, we could have only one with W3 and B3 here. So stacking linear layers one after another doesn't make any sense. Like you could use one bigger layer to do exactly the same thing. That's why we use nonlinearity here to like, so this sort of stuff is happening because applying linear operation after linear operation on a linear operation results in a linear operation. And if you avoid having nonlinearities, we always end up with something linear. And imagine you want to approximate like a sinus. You cannot approximate sinus with a line. You need some nonlinearity. And that's why to make your deep neural network nonlinear, you add this sort of activation functions, which change your fully connected layer from being linear to being nonlinear. So is it clear now also for Zoom how fully connected layer works?
So why it is called fully connected?
Because each node here is connected to all elements in the input.
So there's also something like not fully connected.
Yes. So everything's clear. Is the whole space of Rn explored when weights are updated? Yeah, we say that weights are just metrics, random metrics in Rn. It can be anything. So let's look at example of nonlinearities. So maybe the most common ones that we'll see are these four, this column and this leaky ReLU. And sigmoid is maybe the standard one for old days. Currently, the standard one is the ReLU and leaky ReLU. Basically, like if your element is close to 0, you change it to 0.5. If it's big, you change it to 1. If it's small, you change it to -1. To 0, sorry. In ReLU, if your element is positive, you keep it as is. If it's negative, you change it to 0. And in the leaky ReLU, you like have a small slope that avoids having completely 0 values, but having something smaller, like scaling your value a bit. Let's look at the example with ReLU and some weights. So let's say we have input x as 2 and 1, and our weights matrix is 2, 2, 0, 1, 1, 0. And that's our bias. Then to calculate the result of a fully connected layer, we need to multiply Wx. So we'll get 6, 1, 2. Then we need to add b. We'll get 3, 11, minus 3. And then we want to apply ReLU. Remember that ReLU is max 0, x. So here we have positive value, we keep it as is. Here we have positive value, we keep it as is. Here we have negative value, we replace it with 0. Is it clear? Yeah, good. Is there any guarantee that with nonlinearities can always properly approximate any function? Yes, so regarding that, nice question. So there is one mathematical theory that if you have a lot of layers and all of them are infinity large, so like you do not have like R6 or how many, 1, 2, 3. So R something, you have like R huge, like R infinity, then this multi-layer perceptron can approximate any function, any linear and non-linear function. So there is like mathematical theorem, but the problem is that in reality you cannot allow yourself to have extremely wide neural networks. You just do not have enough memory and compute for this. And also it will be very slow to calculate this sort of stuff. Yeah, thank you for the question. Let me mute someone who is not talking. Yeah, sorry. Yeah, so when you define your fully connected layer, you basically need to define two things. First one is the input size, so what number of nodes you will have as input, and what is your output size, so how many nodes you want to have in the output. Like what is the size of your input vector and what is the size of your output vector after matrix vector multiplication. Just these two values. In the previous example, it was like 2 because we had x to 1, as far as I remember, and output was something with size 3. You also need to choose non-linearity, but in PyTorch, this is a separate entity, meaning that fully connected layer in PyTorch is just this matrix vector multiplication plus bias. And then you choose like ReLU, sigmoid, or something else as another layer. We'll have a look at it in the code today. Is everything clear?
Why would we choose 2 nodes, 3 nodes? What criteria should we use?
So for the input, you know what is the size of your input. You must define input size as the size of your input vector x. Okay. So for the output, if it's your final layer and you, for example, do classification with n classes, you probably want to have output of size n, where each element says, for example, what is the probability of this input being class number, like what ith element in the output vector will tell you the probability of being ith class. Okay, but intermediate layers, they can have any output size or hidden size, so-called, which you can choose. It's up to you. Usually you use like something, a power of 2, like 128 or 256 or 64, something like this. And it's up to you how you design it. So maybe you want to start with something large, like 1024, then decrease to 512, to 128, and then to 2. Or maybe you can make it larger, and then smaller. So I wouldn't say that there is like a recipe which one works better. You maybe just look at some. First of all, you can try anything. Secondly, you just look at what others do in their papers and maybe follow the way how their architectures are defined. Because, for example, for MLPs, it's very standard to use like 128, 128, 128, 2. That's all. Is it clear now?
I think yes.
Yeah.
Is it the same for choosing the activation function, like trying which works?
Yeah, but with activation functions, there is also some theory. So, for example, for sigmoid, it's known that it's not very good because if you calculate its gradient, it will be around 0.5, I guess. And if you stack a lot of layers with sigmoid, the gradients will multiply by 0.5 all the time, and the gradients will become extremely small after a certain number of layers, which leads to so-called vanishing gradients, and your model stops training. And that's why other stuff like ReLU or leaky ReLU were created to avoid these sort of issues. Then after ReLU and leaky ReLU, like you have another type of issue here that at 0 it's not smooth. Yeah, you cannot calculate derivative at 0, so you do some sort of like subgradient or something like this. It's not cool to do it like this. So people created smooth versions of ReLU, like this ELU here or GLU or CLU in common transformers. For many of them, there is some mathematical theory saying that they are cool in certain situations. For example, for CLU, there is a paper with like 10 pages and then 250 pages in appendix explaining why it's cool. It's a funny one. You can just Google CLU appendix. So yeah, I would say that in modern days, you would usually use leaky ReLU all the time and you won't care, or you would use GLU or CLU or Swish if you're working with transformers. You can use CLU all the time, basically maybe for other layers too. I think it will work. So I wouldn't say that it will change a lot if you just go from leaky ReLU to CLU. Maybe the only noticeable change will be going from sigmoid to ReLU and from ReLU to leaky ReLU. Then it's not a so huge change. Yeah, and also there was a question on Zoom, how will the choice of nonlinearity affect the global results? So that's basically this. Like if you choose a sigmoid, you will probably end up with something bad just because of this vanishing gradients problem. Yeah. Do I correctly understand that if I work with 10 by 10 gray images, the input layer will have size 100? Yes. Any questions about fully connected layers? No. Okay. So the problem with fully connected layers is what if you have multidimensional input? Meaning that we have like an image where we basically have a matrix instead of vector. What should we do? One way, as already written by someone in the chat, is to flatten or reshape the whole input to a vector. It's something like this. We have a matrix and we take its first row, then we take its second row and put it here. Then we take its third row and put it here. And the result in a vector. So that's what flattening means. The problem with this is it's extremely memory and computational consuming. Let's imagine that we have 1024 by 1024 image. Then we'll need to process input of size 1 million something. So we will need to have a fully connected layer, which input size is 1 million, and its output size is at least something, but you already need at least 1 million parameters just for your first layer. That's extremely large amount for a single layer. Also, when you flatten the data, you lose spatial information because fully connected layer doesn't know which parts of the vector were next to each other before in the image. So here we know that red and green were close to each other. But here in the vector format, they are far from each other and fully connected layer wouldn't know it. And this is problematic because maybe if you're working like with a dog and we are looking at the dog nose, we know that dog eyes are somewhere around the nose. But fully connected layer wouldn't know it. It doesn't care, it treats all elements as, let's say, independent ones. It forgets about any spatial relations. That's why instead of fully connected layers, when we work with images, we would prefer having convolutional layers. So instead of connecting each node with all others, we apply so-called local filter with trainable weights, which are the same across the whole input. So this is our so-called filter or small matrix, which we train. So here is like weight number 1, weight number 2, weight number 3, etc. Then we take this filter and we overlap it with our image and calculate weighted sum here. Probably it's maybe again better to draw it. Yeah, so again, you have like a filter, let's say values like 1, 1, 1, 2, 2, 2, 1, 1, 2, 3, 2, 2, again, 3. And let's say we have a matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So what we do? We take this filter and we overlap it with our matrix here. And we calculate the weighted sum. Like these two elements are overlapped, so we calculate 1 multiplied by 1. Then 2 is again with 1. So we say 2 multiplied by 1. Here 3, again 1, plus 3 multiplied by 1. Here we say 5 and it's with 2. So we do plus 5 multiplied by 2, plus 6 multiplied by 2, plus 7 multiplied by 3, plus etc. So we also overlap this and this, this and this, this and this. And we calculate our final number. Let's say it's going to be, like, call it x. So we put, like, our final output is x. Then we take our filter. Let's use another color here again. And we move it to the next position, to the next overlap here. And we again calculate the result, which is 2 by 1, plus 3 by 1, plus 4 by 1, plus 6 by 2, plus 7 by 2, plus 8 by 3, etc. And we result in something like y, and our output is a vector with two elements, x, y. Yeah, so basically GIF showing exactly the same thing. Yeah, if you overlap this with this 3 by 3, you will get 6. Then you move it here, you will get -9, etc. So coefficients in this filter are our model parameters. We train them and we modify them with each iteration. So it's going to be like W1, W2, W3, W4, W5, W6, etc. And we modify them with every step we do. Is the output of a single node of a hidden layer a 1D value, meaning that a hidden layer with 10 nodes will produce a 10D array that can be provided as input to the following hidden layer? So output of a fully connected layer is like your matrix vector multiplication. If your matrix has like only one row, your result is scalar value. If you have like two rows, it will be vector of size 2, etc. Yeah, so output of a single hidden layer is going to be always one-dimensional vector. And your input is one-dimensional vector, your output is also one-dimensional vector. Sorry, I got a connection problem. What problems are solved by convolution, please? The problem with convolution, without convolution, with fully connected layer, was that for images or for multidimensional input like matrix, you will need to reshape your input from a matrix to a vector. And this is extremely memory consuming because if you have a large image, your vector will be large and you will need extremely huge fully connected layer. And you lose spatial information. You do not know that this green and red thing are next to each other. Okay. Yeah, so this output of a convolutional layer sometimes is called feature map. just for you to know in the literature. And your input, when you work with images, sometimes may have several channels. Like you work with RGB, red, green, blue images, which you usually have on your computer, which are colored, and there are multiple channels. There are multiple channels there. Or if you work in biology, they usually use like CMYK, which has 4 channels. And you need to somehow process all the channels in your image. So what you do? What do you do? You take one filter for the red channel, another filter with another weights for the green channel, and the third filter for the blue channel. Then you calculate value for all of them, like let's say 120 for the red channel, minus 75 for this channel, and 205 for this channel. And you sum all of them together. So even though your input was with 3 channels, your output is with 1 channel. You collect information from all the channels and put it inside 1 channel. If you want to have multiple output channels, you will need many filters. You will need to stack, like let's say you want to have 4 output layers. This would mean you would need 4 red filters, 4 blue filters, and 4 green filters. And you stack them together to get this 4-channel output after your convolutional layer. Maybe this visualization is not clear, so let's look at this one. Yeah, you want to have 4 output channels, and your input has 3 channels. Then you should have 3 filters for 3 input channels, and these 3 filters will result in a single output channel. To have multiple output channels, you will need several filters with 3 filters inside for each of them. Is it clear? Yeah. Good. I have filters here, basically the same thing as edge weights. Kinda, yeah. But instead, like, you mean in fully connected layers, we had weights as these edges, yeah, as these errors. Now we have these filters as our weights, which we train with our neural network. So to define this convolutional layer, we'll need to choose what is the number of input channels. Like for RGB, it will be 3. For something else, it will be some other number. We need to define output channels. And we'll need to define some arguments which will define the size of this filter. We'll see it on next slides. And of course, we also need to use nonlinearity again, because convolution actually is also a linear operation. So if you do one convolution after another, it's the same as doing one larger convolution again. So we need nonlinearity to make nonlinear approximations too. And again, in PyTorch, they are separate, so you just use the convolutional layer and then you use activation layer. So how we define a filter? At first, we need to define so-called kernel size, which says like what is the size of your filter as a matrix. Yeah, for example, here we have a kernel size 3 by 3. So a 3 by 3 filter. And we see a 3 by 3 square here. Or probably we could have something like 4 by 4. Yeah, and we have this 4 by 4 dark area here. But it could be something with different values for one axis and for another axis. For example, it could be something like 3 by 2. And it would not be a square, it would be a rectangle. It's up to you to design like which size do you want to have. Also, you have a so-called stride, which says what is the length of your jump when you move your filter. So by default, it is 1, meaning that you take your filter and you move it to the next cell, etc. However, maybe you want to skip one column and like jump to through 2 cells. like here on the right. Yeah. So instead of going from this column to this column, we directly go to this one, to the third one. And notice that our feature map becomes smaller because of this, because we like the size of the feature map is how many times we calculated our weighted sum with filter. So because we increase the stride, we are calculating a bit less amount of. So we calculate a bit less, and our output is smaller. Clear? Clear. And probably you want to avoid making it smaller for some sort of tasks, or maybe you want to make it even bigger, or you want to keep it the same as it was before. So if you had like 5 by 5 and you want to have 5 by 5 output, you may want to have padding. So padding can be different. You can pad with zeros, you can pad with some constant value, you can pad with reflection, meaning that this element will be the same as this one. It's again up to you. But the goal of padding is that you add some other values on the corners, on the edges of your input to make filter overlap a bit differently to have a larger feature map. Also, it's good to have padding because notice that your corner element is used only once. Like the first time you have your filter on this corner. And maybe you are losing this information because of this information about the corner. If you have padding, you will use this corner element at least like here, 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 here. So at least 4 times. Maybe it's better for you that you use it more times. Yeah, so what is the purpose of augmenting the size of the stride or add padding? So let's say you are doing like image segmentation. You have an image of a car and you want to highlight what regions on this image belong to a car and what belong to something else. So if you have convolutional layers without stride or padding, you will always decrease the size of your image, while your goal is to have the image of the same size, but with zeros for non-car regions and ones for car regions. So you will have to use some padding or some stride to ensure that your input of your network is the same size as the output of your network. This is really similar to image processing. For example, adding Gaussian filter to blur an image, but the values in the matrix are weights, so it applies to any data. Yeah, so Gaussian filter is basically the same thing, the same convolution, where instead of having trainable weights in your filter, you have Gaussian like this like mean sigma thing. But the way it was, what it's doing is exactly the same thing. Yeah. So you can apply it to any type of data. Actually, you can be like we are currently looking at 2-dimensional stuff, but it can be 1-dimensional, 3-dimensional, etc. Yeah. One theoretical thing, which you also may find in some papers, is called receptive field. It's the part of the original input the current element depends on. For example, to calculate this element, we had to calculate all of this, and we had to calculate all of this, because to calculate all of this, we need to calculate all of this. Or for example, to calculate only this element, we didn't need to have the whole input. We could have only this red part on the left. So the goal of receptive field is to say how much of your input data contribute to your output. And probably you want your output to depend on the whole input, so your receptive field to be as as high as possible. Yeah. And one last parameter of a convolutional layer is called dilation. It's a bit strange one. So basically you have the same filter, like 3 by 3, but now you want to split elements inside your filter. So if you have a dilation 2, your filter will skip one column and move to the next one. So you have this type of grid instead of a square. Got it? Would detection work at the same level without padding as with it? So for example, if we are looking for a cat and we see only half of it on the edge of the photo without padding, we will miss it. But if with it, the filter will activate those at half the power than if we see the whole face. Would detection at the same level without padding? You mean so like if we miss part of a cat because we didn't have padding, because we didn't use element, like because element was the cat was at the corner, that the detection can work worse. Yeah, this can be a thing. So dilation would be useful when images are very high resolution in case of image recognition. So dilation would be helpful, yeah, when you want to increase this receptive field. So you want to increase the dependency of your output, like on how much data it depends on your input, without increasing the computational costs. Because if you increase the dilation, this is a one-dimensional case, similar thing. So your output here depends on all this input data, just because of dilation. If you wanted to do the same thing without dilation, you would need to have like more layers, or you would need to have larger convolution, which is more expensive. And probably it wouldn't capture local changes so well. So for example, here, there is no dilation on the first layer, but then there is dilation 2, so we skip one node and we go to another. Here is dilation 4, we skip 3 nodes, and here is dilation 8. And because of this dilation, this element has very huge receptive field. If you're wondering like why all arrows are like this on the left, there are no arrows on the right, that's because we use so-called casual convolutions, like we do not want to look at the future. This is useful, for example, for audio. When you want to generate a continuation of your audio sequence, you do not know the future yet to generate it. So you only look back. And that's why you use causal convolutions. So dilation, when images are, yeah, so I guess this is clear now. You mentioned only the purpose of padding of saving the size, but does it affect the quality of detection? So I think it may detect the quality of detection if your object is located on the edges, but maybe it's a rare case. That's the first thing. Secondly, I think like if it's not the rare case for your task, you would probably want to have like padding for your input. Okay. What is the dilation? So I guess now it should be clear. As far as I know, padding is critical for information passing layer to layer, especially in deeper layers, like small feature map is earlier is most trivial. It's when you put space in between convolution to augment the output size, I think. What is the receptive field? Again, so receptive field is how your output, like on what elements in your input, this one, so what elements in your input contribute to calculating this output. So for this red point, we need to know only this part of the input. And for this point, we need to know the whole input to calculate it. So that's what is the receptive field. And because receptive fields basically means how much information you use to make your decision, you probably want to have a higher receptive field. Yeah, and yeah, dilation again, you put space in between elements in your filter to increase this receptive field. Yeah.
Can I go back to the slides? Yeah, so what are the colors representing the yellow?
So the red one says like, okay, this element looks at something what is, no. I think here, yeah, red one is just to highlight that this red one is looking at this red one. Here, I would say it should be yellow, actually. To say that this one looks at all these elements, which looks at all these elements. So this one should be yellow, sorry. Clear? Questions? No. Is it always better to have a large receptive field? Not exactly. So at the beginning, you probably want to look at some local dependencies. But then when you go deeper, you want to also capture some global context. And so when you go deeper, you increase your receptive field. But when you start working with images, you probably want to have something local. That's also related to this fully connected layers issue. Because fully connected layer looks at all input at the same time. It doesn't care about like spatial relations, what is close to each other, what is far from each other. But you want to have this sort of information. You want to know like whether you look at the nose of a dog and whether like there are eyes next to the dog nose, or maybe the eyes are missing or something is missing. Or for example, you look at the wheel and you look a bit on top of it to understand whether this is a motorbike or whether this is a car, something like this. You do not want to look at the whole image at first because it would be very hard to capture this sort of local information. Yeah, so one thing that is similar to convolutional layers is called pooling layers. That's exactly the same thing, but we have fixed parameters instead of learnable parameters. For example, we can have max pooling where instead of applying filter and taking average, we take the maximum element. So we again overlap our filter with our input, but we take the maximum value. Like let's say 8 here, 7 here, etc. Or we could calculate average, but without trainable weights. We just use a uniform average, like where like the weight is always like 1/4 for a filter 2x2. So the goal of it is to usually to reduce the spatial dimensions without adding new weights, without making your neural network more complicated. Clear?
So this pooling layer is basically something similar to the activation function that you mentioned.
I wouldn't say that like it of course makes your so some pooling layers may make your function nonlinear, but the goal is a bit different. So nonlinearity makes your function nonlinear to avoid stacking linear layers, which would end up in something which is linear.
For the architecture.
For the architecture point of view, so activation is applied element-wise. For all elements, you apply the same activation, which is applied on a scalar value. Here, you apply it on several values, which are inside your filter. So it's not exactly the same thing. But what is similar is that you do not have any trainable parameters.
And this feature map is from the what's the name?
So this feature map was a result of a convolutional layer, and then you apply like a pooling layer. One remark is that you can have trainable parameters inside your activation function, like p-relu, for example. but let's avoid stuff like this for now. What is a feature map? Feature map is the output of a convolutional layer. Sometimes it's called feature map. So your convolutional neural network usually looks like this. Like you have your input, then you apply convolution plus nonlinearity, then probably you apply some pooling to just reduce the dimensions. Maybe then again some convolution, maybe some other pooling. And if you want, for example, do classification of your image, after a certain number of convolutions, you have like a very compressed representation, which you can flatten into a vector and then apply some fully connected layers like this. And the output of this fully connected layer will be like, let's say, a vector of size n if you have n classes. And you do classification with these n classes. Questions? No? Good. Yeah, so we covered what is a convolution, what is a fully connected layer. And one important thing which we want to cover today is called residual connections. To understand why we need them, let's recall what is backpropagation. Yeah, we had our input layer, we calculated its output, we calculated loss, calculated gradient, and propagated this gradient back through this computational graph, like from here to here, to here, to here. So the gradients, they go from deeper layers to the first layers. The problem is that every time you go from something deep to something which wasn't so deep, you multiply your gradient with something. Like, for example, for sigmoid, as I already mentioned, you would multiply it by something close to 0.5, for example, in terms of like vector norm. So if you have a lot of layers, one after another, the gradient may die before it arrives at your first layers of your model. Yeah, so if you have a lot of layers like this, the gradient will start here and it will be like nice gradient with huge values. Then it becomes smaller, 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 and your input layer may have gradient close to 0, so your weights wouldn't change. And this is problematic. So this problem is called vanishing gradients. And if you have vanishing gradients, your weights do not change. And if your weights do not change, you are not basically training. So you apply some random operation, your model performs poorly. There is another problem called exploding gradient. We won't cover it, but that's like a vice versa thing, where your gradients become larger and larger all the time. One way how it can happen, for example, you forgot about optimizer.0grad, which we covered yesterday, and you accumulate your gradients all the time, and they become larger, larger, and larger, and they die. Something like this. So even if we don't have gradients problem, stacking too many layers may lead to quality degradation. So it was shown empirically that if you have like a small model, you train it, you measure its quality, then you use exactly the same architecture, but between output and small model, you add some other layers, the model for some reason starts performing poorly. While intuitively, it should not. Why? Because these intermediate layers that you added should at least perform as well as identity layers. Meaning that, like imagine your architecture, your large architecture can learn any function. Yeah, so at least it should learn training, it should learn becoming identity layers for this intermediate part. Oh, sorry. I don't get how sigmoid makes gradients move. Yeah, so how sigmoid makes gradient smaller is about some mathematical stuff. Just calculate the gradient of sigmoid and look at its mathematical norm. It will be around 0.5, meaning that if you multiply by 0.5 all the time, you get vanishing gradients. So, and for this, let me maybe draw it again to make it clear. Let's say you have your neural network, which looks like input, like your model, output. Let's say we have big neural network, and we have the same input, then we have the same model. In terms of architecture, I mean like the same fully connected layers or the same convolutional layers. And then we have like, let's say model 2. And only then we have out. Then we are training this big neural network, and intuitively, it's always possible to make it work like, let's say this is model X, this is model Y, this is model 2. So intuitively, we can always achieve model X equal model Y and model 2 equal identity, meaning that model 2 applied on some input returns input, so it doesn't do anything. Okay, is it clear for you why it's always intuitively possible to have such a model? Yeah, because like model X and model Y have exactly the same architecture. You train them exactly in the same way, and you just add some new layers here. These new layers is just some other like fully connected or convolutional layers. And these fully connected or convolutional layers, in theory, should be able to learn identity mapping, like to learn changing, going from X to X. But the problem is that in practice, it doesn't work, as already people mentioned in the chat. It's clear, yeah, why we kind of have this. Yeah, good. In theory, we should be able to do this. And this means that our big model should perform at least as well as our small model. In practice, it is not always true. In practice, this big model can perform much worse than the smaller one. The reason for this is because actually it becomes hard for the model to train it, and we want to train to get this identity mapping and to learn something to increase its quality. And we want to somehow help our model to understand that at least it can do this identity mapping. How we can do it? We can say, let's go from layer 2 directly to layer 4. So if layer 3 and layer 4 do not want to do anything, they would, like layer 4 would say, okay, I would use my input from layer 2, layer 3, I wouldn't use it. And it would be easier for this output to depend solely on layer 2 instead of layer 3 and layer 4. Because instead of going like from this to this to this, it can go from this directly to layer 2. You see it? So this allows the model to understand that it can learn identity mapping. And secondly, it allows the gradients to flow better, because if you have this vanishing gradients problem, that happened because it took a lot of steps before going from here to here. Now you can jump directly from here to here via this new arrow that you have. And this would improve the gradient flow for this layer. So when your layer uses output of previous layers, this is called residual connection. So this arrow is residual. Clear? So one neural network that made a lot of impact in the world by like creating this idea is called ResNet, and it says that we can have this sort of so-called res block where we have our input, we have our identity residual connection here, and inside we have like convolution, ReLU, convolution, and then we just sum and apply ReLU at the end. So why ResNet is so important? Because it was proposed like in 2015, but people still use it or its variants today in many applications, and it still may be the state of the art for this type of applications. But our model always, unless it's enormous comparing to data, wants to overfit. We don't use layer 3 at all, or we use layer 2 output and layer 3. No, so here we use layer 2 and layer 3 output together. When I say that it's easier to learn identity mapping, I say that if neural network wants to skip layer 3, it would be easier for it to skip it. If it doesn't want to skip it, it won't skip it. But we want to help our neural network to be able to at least achieve the same quality as a small model. I said that if it's not for model to use less layers, it can skip layers at will. Yeah, kind of. So the larger the model, the easier for it to overfit on your data, and that's why also your quality on test data may decrease. And when you have these residual connections, you at least can maybe learn this identity mapping, and you're less. So the chance of you being overfitted on your training data is smaller. If I understand well, the residual connection allows our model to skip a layer if the layer is permitting worse than identity. Kinda. So in reality, so intuition is like this. In reality, they are not like both of them will be used to calculate layer 4. They are not identity. Like this one is not identity, this one is not identity. But it's easier for model to understand that it should achieve at least the quality of the small model. Can it be worse? Yeah, one layer can perform worse than having an identity layer. That's true. How can the model know when to skip the layer? So when I say skip, it doesn't mean that it's like completely avoids layer 3 output. I mean that like you have some sort of weights. Yeah, if your model thinks that these weights are not important, it would make these weights close to 0 by updating your model with this gradient descent thing. So like here is the intuition. Then you do this gradient descent optimization, and your model updates the weights according to your data, to your inputs and your desired outputs, and it will learn like whether to use something or to use it less, what weights to choose. If it achieves less quality than identity, why don't we just get rid of the layer? The thing is that after you add residual connections, you actually increase the quality of your model here. So you add residual connections. Like before, when you didn't have residual connections, your quality of your deep neural network with 34 layers was worse than the same network with 18 layers. So you had quality degradation. After you added these residual connections, you started to perform better. So residual connections intuitively allow you to perform as good as small models, but in reality, they perform even better because of this better gradient floor and because they are not, they're more robust against this degradation problem. So with residual connection at a layer, we can have a choice between two gradients and hence two update ways. Choose one which leads to a more significant update. No, with residual connection at a layer, we have gradient here and gradient here. We sum up them, but maybe this gradient was small, this gradient was big. So this has like more importance, or maybe vice versa. It's up to the model and your data, like which one will be higher. You are not skipping them. You're not like saying, okay, I won't use this one. I will use only this one. You use both. The thing is just one can be smaller, one can be bigger. Why is Zedin's identity useful in ResNet? Because intuitively, you tell your model that like, hey, I add more layers like layer 3 and layer 4, but you should use them to improve your model, not to make it more complicated. Yeah, to like, if you feel like identity is okay, just use this another error and forget about having layer 3 in between. So that's a sort of intuition you should have. Yeah, also another block in ResNet was, yeah, so this standard block, another was something like this. When you have extremely large neural network, you have a lot of channels, and you probably do not want to use convolutions with extremely huge number of channels. It's computationally expensive. So what they suggested to do, suggested to use this so-called bottleneck layer, where you at first decrease the number of channels with one-to-one, one-by-one convolution. Then you do some sort of operation inside this small representation, and then you convert it back to this huge 256 dimension via another one-by-one convolution. So this has the same time complexity as this one, but it operates on a higher dimensional channel, so meaning that it can like use more information and achieve better quality. And your ResNet looks something like this, where you just stack these residual connections with a lot of convolutions, and you do it many, many times. And actually, like you can do at first addition, then you can do ReLU, or you can do ReLU, and then you can do addition. Like this was the original design. This was the design proposed in another paper. So this one actually works even better, as shown here. But the idea is exactly the same. Clear? Clear. Yeah. So why do we like ResNet? Because we can train it once and then utilize it for any downstream tasks that we want, using the same pre-trained weights that we had. What do I mean? So there is an idea of I'm sorry, can you explain how the bottleneck improves time calculation? So if you had it like this on the left, you would have 3 by 3 and 256 channels, then 3 by 3 and 256 channels. It's very time consuming to calculate 256 channels to get one output channel. And you would need to calculate like 256 output channels. So this is very expensive to do these many calculations. So what they suggest, they say, we do not want to calculate anything in 256 dimensionality. Let's reduce the dimensions, do calculations inside this reduced dimension, and then go back to our original 256 dimension. So this has the same quality, but is much faster to do and saves you memory and speed, memory and time. Yeah. So what is fine tuning? So imagine you trained a model on classification of dogs and cats, and you can do it pretty well. Then you want to use some model to do some biological stuff, for example, to understand whether the plant is okay or whether the plant has some disease. And probably you could just use one model and train it from scratch on this data. The problem would be that it's much easier to take a lot of photos of dogs and cats and other objects rather than collecting a whole data set of plants and their diseases. And if you do not have a huge amount of data, your model can perform poorly just because it didn't see a lot of differences, like a lot of types of possible inputs. So what people do, they use some large models on some large data sets where the data is the data distribution is very wide in the sense that like there are a lot of types of possible like types of images, let's say, and then they copy weights plus train with small learning rate on your small data set for your specific task, like having the plants with diseases. And the thing is that your model will actually perform better when you use these pre-trained weights, when you just copy weights. Why do we use small learning rate? Because if we use high learning rate, we would jump from copied weights to something which is far from the original weights. And we lose all our benefit from having something pre-trained. So we do not want to jump too far. We want to adjust our model to this new data. We do not want to jump from it directly to something random. Yeah, so when do we use it? When tasks are similar, the learned features from one task can be helpful for another task. For example, if we know how to classify dogs and cats, we probably look at, for example, ears. Yeah, they have different ears. And then we probably want to calculate, to classify, let's say, goats and like zebras. And we may also want to look at the ears. And our model already knows how to find ears on the image, let's say. So these sort of features can be helpful from one task to another task. And if the data set for your specific task is small, it's better to use some pre-trained knowledge because it's hard for you to collect new data. And having more data is always beneficial. So you train your model on some other task which has larger data, and then use this model as a starting point. So your pipeline is pre-train on another task on large amount of data, use the same model. You can change like some layers. Probably you will change final decision layer, load its weights, so meaning start from this pre-trained data. And then you set learning rate to some small value like 1e-5 or 1e-6 and train on this new data set. Why would you want to change like the last layer? Because if the pre-training task, for example, has 1,000 classes, and you now do plant diseases where you only have 2 classes, like normal plant and disease plant, you want to have an output layer with only which output will be a size of 2. So you would need to replace the final layer of your neural network from fully connected layer with 1,000 output classes to fully connected layer with 2 classes. And you cannot use the same layer, yeah, so you replace it with a new one. Let's look at examples when it can help. For example, you want to detect defects with English speech. There are a lot of data sets in English to do this, and you train very cool models that can do everything. But then you want to do the same thing with Russian speech, and with Russian speech, probably there are not so many defects available online. So instead of training from scratch on Russian data, you take your English model and you fine-tune it on small amount of Russian data. And now you have something which performs well on Russian language. Or you do some image segmentation on like dogs, humans, cats, or cars, and then you want to do some medical image segmentation on brains or something else. And again, collecting medical data is much harder than collecting like cars and something else. So you pre-train your model on this sort of data and then copy your weights to use it on this sort of data. Clear? Yes.
So you use copy bits that we do not copy other bits. We need to select something.
So usually we copy all the weights except for maybe the last layer, which we change because we have different number of classes. But for some tasks, we may copy all the layers. For example, when we use the model just as a so-called feature extractor. So we use this, let's say, ResNet, and then we add new layers on top, but we do not modify ResNet. We maybe throw the last layer because we are not doing classification anymore. We put layers on top. So this can be useful, for example, when your model knows how to do image classification, it basically knows how to create a compressed representation of your input in a format which can describe your input very well. So then if you have some other task, maybe not classification, but something else, like what? Like audio-visual speech-to-text, let's say. So my image model, like ResNet, would look at my mouse and it would compress it into some vector. Then I can use another layers on top of it to extract which words did I say from this compressed representation. And I could pre-train my model just on my mouse and then fine-tune it with some extra layers to do another sort of task, not classification anymore, but speech recognition. Okay? Cool. People on Zoom, any questions? No. Yeah, so that's all for the lecture. Remove people in the next sentence using, okay, yeah. So, Melodies, you had a question, please write it down. Was the ReLU? Could you briefly repeat the essence of ReLU and loss there to avoid linearity? Yeah, I've kind of meant what does it do exactly? Basically, this is what we use to skip layers or something. No, ReLU is activation function. We do it element-wise, and if element is positive, we keep it. If it's negative, we make it 0. That's basically what it does, yeah. About proposed ResNet architecture, what does the weights block do? This weight layer, you mean? So this is some convolution like this one. 3x3 convolution with 64 channels. Or 3x3 convolution with something else. So it's better to see here. Yeah, you have convolution with this number of output channels, convolution with this number of output channels, etc. You can participate using voice chat too, yeah.
Yeah, and can you then come back to the difference of proposed and original?
This one?
Yeah.
So here weight is again convolution, like 3x3 filter with something, with some number of channels. The difference is that here we do convolution, ReLU convolution, and then we do this residual connection, and then we do ReLU. And here we say, let's put ReLU like before addition.
Yeah, okay,
here.
and what is BN?
Batch norm, we'll cover it tomorrow.
Yeah, okay, thank you.
So what is ResBlock? I guess it's clear now, yeah? ResBlock is just this sort of stuff. The general idea of causal convolution was that you do not want to look at the future because maybe like you are doing something like audio generation, and you only know what was in the past. You cannot predict future by knowing the future. It would be strange. So that's why you use causal convolution, meaning that you can only look at the past. Channels, number of filters, and convolution filter itself. Yeah. So 3 by 3, it's convolutional size, for size of the filter. Number of channels, it's number of these filters.
Yeah. If we try and take a look at the slides on our own later and we don't understand something, is ChatGPT or any AI tool useful to explain things?
I would say it would help a lot, yeah, because it's it's a basic stuff, so it should explain it well. But probably use like 4.0 or something like this. Use like not 3.5, but 4.0.
Okay.
But maybe 3.5 will do something reasonable.
Is Copilot good for that?
No, Copilot is for coding probably mostly, not for explain. But you use free ChatGPT. It has several number of prompts per day which are free. How we compute the number of parameters of this model? So for fully connected layers, is basically the size of your matrix and the size of your bias. For convolutional layers, the number of parameters is the number of filters multiplied by the size of the filter. Can you briefly describe the place of a seminar later? So why ResNet is still popular if it's not effective? So what is 3 by 3? 3 by 3 is the size of the filter, 64 number of channels. So why ResNet is still popular if it's not effective? No, it's so first of all, when people say ResNet, they use usually the second version, which is this one, where ReLU is before, or ReLU is here and not here. That's the first thing. And secondly, it's like, of course, this thing is better than this one, as we see from the plot. Still, it's extremely cool. Like you pre-train it on a large amount of data and it performs extremely well. Or a real example of what you can do with like how to create a model and how to train it. So last time we did stuff like this, where we said, okay, we have our function. Let's start from a random point and try to optimize our model to go like from here to here, to optimize our starting position. And we had a for loop like this, where we at first calculated like the value of our function, then did backward operation, applied optimizer step to change the starting position, and basically we plotted something like this. And now we'll see that when you have a deep neural network, you basically apply exactly the same for loop. But to do this, we need at first to understand how to create a model. So in PyTorch, all models are instances of the class torch.nm.model. So to create your model, you need to do the two steps. First one, define network layers. And secondly, define the forward step, meaning define how your input will be processed by your layers to get your layer output or your model output. So it works as a __ call, meaning that instead of doing model.forward, like here, you can just do it like this without .forward. It will apply forward automatically. So note that you do not need to define backward step because PyTorch handles it for you. So it knows that if you use like linear layer or something like this, the backward layer is standard. The backward step is standard and it's predefined, and it's easy to like it can calculate it automatically. So in rare cases, you may want to change backward and write it yourself. You can do it if you want to, but you need to understand why you are doing it. So for now, let's say that you never want to change the backward step. And when in the future will work for something, you will think that I need some custom backward, you will just do it and you will know how to do it. So the most popular layers are predefined in torch.nn.model. You can see documentation. For linear layer, which is also known as just fully connected layer, as we discussed, you use nn.linear. For convolutional layers, you use nn.1D if you have one-dimensional convolution. So you work with like vectors. nn.conv2D when you work with matrices like images. 3D when you work with some 3D data. But most likely you won't use nn.conv3D because it's extremely time consuming and computationally consuming. So when you work with 3D data, sometimes you use conv3D, but most of the time you would try to find a way to avoid it, to maybe stack with nn.conv2D and do some tricks. Yeah, there are some max pooling layers, average pooling layers, and many other. So to define our model, we need to create a subclass of torch.nn.model and define forward step. So we import nn, and we create a class which we call like my model or some any other name, and we inherit from nn.model master class. In the def init, we pass some arguments that we want to use to define our model. For example, this can be number of channels for convolutional layers or number of like vector sizes for your linear layers, etc. But before you define any variable, you should call super.init. What this does, so if you know Python, you probably know, like if you are not like an expert in Python. But so this calls init from the master class, from nn.model. So this init initializes everything PyTorch needs to then work with your neural network as a deep neural network class. So just when you start, you always call this, and then you create any variables. So to create like a layer, we say self.layer name, let's say net1 equal, and for example, we want to create a fully connected layer. We say nn.linear, and then we pass input size and hidden size. We could do it as a key arguments like input features, out features, something like this. Or if we avoid keyword arguments, it will just automatically understand by the order of elements that the first one is about input features, the second one is about output features. Then, as I said, we need to define activation layer, activation function. And because it's separate from linear, we do it as another variable here. We then create another hidden layer, and then we create an output layer with output size. How to define forward? We have our input data, and we need to say how to process it. Mark, можешь закрыть, пожалуйста? So we say, okay, let's say some variable x is self.net1 on input data. Then we use the same x and pass it through net2, through net3, through net4, and to finally get our output, we pass it through net5, and we return it. So that's our forward function. Now we can try to create an instance of our class and run it. Any questions until now? Clear? Yeah, so we say, let's have input size of 10, hidden size, so like all our inputs are converted to 128 vector, then again to 128 vector, and then to a vector of size 2, because we say like output size is 2 here. And we can print our model to see like what layers this model has. We see its name and we see name of each layer and what type it like this layer is. So it's linear with these input features, with this number of output features, and we also see that there is bias. Now let's create some random vector as to showcase how to work with some input. We create example tensor, we do model example tensor, and we get output. Output is of size 2, so only 2 values. And this is because our output size was 2, as we just defined here. Note that we wrote something like this, and then applied everything sequentially, like one after another. So because this operation is common, PyTorch has predefined classes to do this kind of forward step for us automatically. So to do so, we need to put all these layers inside NN.sequential. So instead of having net1, net2, net5, we say self.net equal NN.sequential and put this 1, 2, etc. 5 layers here, one after another. Now in forward, instead of having all these repeated elements one after another, we just call self.net input data and we get the same result. And if you print our model, we'll see that it looks similar as before, but now we have net here and it's written that it's sequential here. Sequential means that it is applied one after another. Again, we calculate it and see some output. Note that there are like an n.model list and n.model dict, which you may find useful in some certain cases, but most likely, like you will, like the most common one that you will use is an n.sequential. So note that it's not mandatory to have like one class where you define everything. Probably you want to define some subclasses for your parts of models that you use commonly. For example, you have this res block that I showed you during the lecture, and you don't want to write forward step for res block all the time from scratch. You want to define res block once and then use it as a new type of layer. Like, so remember we had this kind of stuff, yeah? So we could write res block as sinus x2 multiplied by y as 2 layers, or we could use it as 1 layer, which does the same thing, but is a single function. To do so in PyTorch, we say, let's create subclass, which we call, for example, my custom layer, do exactly the same thing as before, define init and forward. And now in our big model, we can directly use this subclass. So previously we had nn.linear relu, nn.linear relu. Now we have my custom layer, and nn.linear. And this nn.linear and relu are inside my custom layer. Is it clear?
So can we use multiple sequential layers?
Inside one another? So it would be strange to use one inside another because it's like a long sequential. But yeah, PyTorch won't stop it. Yeah, and we can have a look at how this model looks like. You have the same net, but you only have 2 sequential layers. First, my custom layer, second, my custom layer. No, three, sorry. And the last linear. And this my custom layer itself consists of another layer, which is also an sequential. Clear? Now, we saw that our model actually does the same thing, but output is different. I don't know if you noticed it, but let's create our model and run it twice on the same tensor. Notice that the output here and here is different. This is because our model is initialized randomly. So you start from a random position, and then you optimize to find some optimal position where your model performs well. So if you do not fix seed, so you do not fix how your randomness works, you will always end up with a new starting position. And this is bad for you because imagine you like wrote a lot of code, you trained your model like for 20 hours, and then you want to reproduce your results. You want to train it again and get the same result. And suddenly you do not get the same result just because you start from a new position. Because you didn't fix the seed and you start from something random, which is different from what it was before. So in terms of having reproducible results, it's always better to fix random seed, and you can do it like this. Let's keep it for now. You can look at it at home, but this type of stuff, fixed randomness for all models that could lead to something random. One thing that I might need to explain is what is deterministic here. So PyTorch may use different algorithms depending on your hardware, on your GPU. Like if you have something modern, it can work in one way, it can have something old, it can work in another way. And also, it can use some algorithms which are not precise, which are a bit random to make operations faster. So by default, it uses this kind of random operations. And this may also lead to having slightly different results in your output. So you do codename.deterministic equals true to ensure that you have deterministic results. And you do codename.matchmark equal false to avoid having differences between new GPUs and old GPUs. However, this may lead to being a bit slower in training. So most people do not care about this benchmark equal false because it would make their trainings much slower. So we fixed all the seeds, and we had 3 different versions of our model, and they all perform differently because of this randomness, even though inside they do exactly the same operations. So we can make them to do this, to have exactly the same. Maybe I should use it like this. Sorry. So let's run it like this. Here we see a different output here because we didn't fix the seed. Now let me copy this and edit. I will use some seed. And let me put it before every model that I use and try if it's gonna help. So you see, I fixed the seed and now everything performs exactly the same. So that's one way of having reproducible results. Another way is to manually set your weights to some value. And here I just show how to do it. We iterate over all layers that we have. And for example, for linear layer, we can get its weight matrix W and its bias by doing model.weight and model.bias.data. And we initialize it with all ones. It's better to do all ones, and it's better to do constant values, but so never do it. But for the sake of showing what we can achieve, I showed here and we get again the same results. Good? Questions? No. Questions on Zoom. How do we calculate backward for our own layer? Yeah, so for our custom layers, backward is handled by PyTorch itself automatically. So PyTorch knows what is backward for nn.linear. It knows what is backward for nn.relu, and it knows that like one after another, like you just propagate this gradient via propagation algorithm and chain rule. Okay. Yeah, so we had this example with training our function, finding this optimal solution. And now we want to do the same with deep neural network. So first thing we'll need to do is to find the data set. And when we have a data set, we may want to apply some augmentations, as I said during the first day, like you want to crop an image or rotate an image. And you can do it inside your dataset class, which we covered yesterday. So I will remind you that we have a dataset that we will need to define init, get item, and len. Get item says how to access the ice element of your dataset. And now we can maybe do some pre-processing inside, like we can define our own method pre-process. Let's say it would, for example, subtract of 300. And we could apply transforms, which could be like this cropping, rotation, something like this. And we can make it custom in a sense that if we didn't pass any transform, we do not apply it. If we passed it, we apply it. And we just have if-else statement here. And let's say we had our random data set. We can get its ice element. And let's say our transform is multiplying value by 2. And we see that before we didn't have any transform, so the values were around 300, minus 300. And now because we added transform which does multiplication by 2, values are around minus 600. Clear? Clear. So one data set that people usually use is called MNIST. It's a toy example where you have an image of a digit, like 1, 0, 1, 2, 3, etc., 9, written by hand. And your goal is to classify whether it's like 0, whether it's 1, etc. So you have 10 classes and handwritten images of these digits. And to work with images, you most likely would want to use a library called Torch Vision. So it's Torch sub-library for vision for tasks related to images. Yeah, so in Torch Vision, you can create custom transforms, or you can combine several transforms one after another using torchvision.transforms.compose. You say, I want to apply this transform, then afterwards I want to apply this transform, and then I want to apply this transform sequentially. So here we apply only one transform, which is conversion from image format to tensor format, but we could have something like, let's say, random crop. We would say that we would want to crop our image to something like of size 12 by 12. And then maybe we would want to have some other augmentation like random rotation. Like random rotation, we would want to rotate our image by like 90 degrees, let's say. Let me use like this to just show how it works. Yeah, so in Torch Vision, there are several predefined data sets and MNIST is included. And here you do not need to write this custom class just because Torch Vision already wrote it for you. So you can just download it inside this MNIST directory. You can say train equal true to download train set or train equal false to download validation set. You say download equal true if you haven't downloaded it before. And you can pass transforms that you use, like rotation, conversion to tensor, etc. So here is our image. And if I click on it several times, it always gets a bit rotated. That's because we had random rotation here. Yeah, you see, so it's rotated again, rotated again. And if I remove this rotation, it would always stay the same. Clear? So all the data set will be rotated or only some batches. Yeah. So every element will be rotated because it's like self-transform here, but it will be rotated by a different degree because random rotation, it chooses like random degree between 0 and 90, which we passed here. So now we want to work with batches because we want to use this mini batch gradient descent where we pass several images, combine them into one huge tensor and work with it. To do it, we need data loader, and we pass data set and say what batch size we should use. We also say shuffle equal true to shuffle the training set. Why do we use it? Because maybe, let's say our data set is stored in a such way that all zeros are in all like first 1000 files are all zeros, then all second 1000 files are all ones, third 1000 files are all twos, etc. So maybe your model, instead of learning what makes your image look like this specific digit, it would learn the position of this element inside your, like on your disk. And it would learn some information which is not actually related to the image itself. It's some like feature which you added yourself by the way how you stored your data. And actually, there was a story of how one guy won a medal on Kaggle in some challenge by just looking at the order of files because people didn't like shuffle them. And it occurs that like if you just use the index of the element in your data, it performs much better than all other models. Yeah. So it's always important to shuffle your training data to avoid this kind of artifacts. And you will have len dataset divided by batch size, number of elements, number of batches inside your data loader. And if it's not divisible by batch size, then some part of your dataset will be skipped, like the last part of your dataset will be skipped. If you do not want to skip it, you should say drop last equal false. See, so if I do it right now, I would say I would get all images, all 469 batches. If I do it true, I will get 468 batches because I skipped the last batch. When it's useful when you want to avoid having one batch that is much smaller than all other batches. For example, here, like your one batch could be of size 128, another was of size 96. 96 is probably okay, but if it was like something like 2 or 1, you probably would better for you to skip this batch completely. Clear? Yeah, so we are close to the end, hopefully. Yeah, I will show you 3 examples of the same model, not the same model, but how to create fully connected model, as we discussed in lecture, how to create convolutional model, and how to create ResNet. So for fully connected network, we already did it. We call a net.flatten to reshape image into a vector because we cannot work with matrix, we need vector. So we call a net.flatten here. And then we apply just some linear ReLU, linear stuff. For convolutional network, we do not need any flatten. We just use conv2d. We need to define input channels. And our image is RGB, so we have like 3 input channels. We define some hidden channels. It's our choice. For example, we can say, like, let's use 32 hidden channels. And we define kernel size. Here I'm using 3 by 3 with padding 1. It's again just my choice. So did the loader separate data set on batches, or it gets random batches and elements can be repeated? It separates data set on batches. Yeah, so it first shuffles the data set and then takes random batches. Elements won't be repeated until you reuse the data loader in the next epoch. Or until if you want to make like your data load infinite, you will have an example of this on Friday. Yeah, so convolutional network basically looks exactly the same, but you have const2d instead of linear. Clear? Yeah. And for ResNet, you want to create a custom res block where again you have this const2d stuff, which is basically so we want to create this layer. Yeah, so we need const2d, relu, identity, and again relu. So I am creating const2d, relu, and also here I'm introducing another convolution called downsample. It's used when you cannot directly do identity here because the shape here is probably a bit different from shape here. It happens when, for example, you had like 3 channels here and 64 channels here just because you wanted to increase the number of channels. Then you cannot use identity. You would need to use convolution, which would transform your input from RGB to having 32 channels. And we do it here. We say that if input channels are not the same as hidden channels, we create a downsample convolution with a kernel size 1. So we just convert each element with the kernel size 1 by 1 to make to just change the number of channels. So yeah, and in forward step, we just apply our convolutions on X. This is this direction. My messages are not updated. Oh, that's okay. No. Kernel size is the size of a filter. Like 3 by 3. Like 3 by 3. Or 4 by 4. Stuff like this. Yeah, so our residual connections are just here, output plus X. That's all. And if there is a channels mismatch, we do downsample here in advance. So we have now our ResNet-like network where we have res block. After several convolutions, we have already nice representations. We do nn.flatten to get a vector and to apply final nn.linear to do some sort of classification. And we can print this network. They look like this. Like this is our ResNet. This is our convolution. This is our linear network. And we basically finish with our data set and model. All we need to define is our loss and our training loop. So for the loop, for the loss, we define this criterion, which is cross entropy loss, which is used for classification. We didn't cover it, but we had an example with mean squared error yesterday, where fx minus y and everything in square. So this is a similar thing, but more common when you work with classification problems. Yeah, and here I use this thing just to show progress bar. Ignore it for now. So our one epoch looks like before. We iterate over our data loader. We get image and label, like what digit, what is the ground truth digit label. We operate, well, we run our model on this image to get output. This is our forward step. Then we calculate loss by comparing our output with the ground truth label. We apply loss.backward to calculate gradient, optimizer.step to update model weights, and optimizer.zeroGrad to zero the gradients to avoid the accumulation as we discussed yesterday. And we also update our learning rate by doing scheduler.step. And here we just calculate some metrics for us to visualize how we progress, how we improve, to see that the loss is going down. So these two stuff, these two lines are just to return loss to see how well we are doing. But it's exactly the same thing as we had yesterday when we had a function. Now we just have model instead of this f, and our data is image and label. You may wonder what is model.train. So when we train our model, we want to call model.train before, and when we evaluate our model, we want to call model.eval. This says that some layers, which we'll cover, for example, tomorrow, like batch norm, they operate a bit differently during training and during inference. So we want to say, hey, PyTorch, like use evaluation mode for this layer if you are doing evaluation, and use training mode for this layer if you are in training. What our X looks like before .flat, and it's some matrix which looks like some random stuff. Because it's in some latent representation of our original image. So for the evaluation, we do exactly the same thing, but we called model.eval. We again calculate model image and calculate criterion. And now we calculate some other metrics. Instead of loss, we also calculate accuracy, which we discussed yesterday again. So this shows how many times we match exactly our predicted label exactly matches the ground truth label. Yeah, I guess I have one mistake here. I should do it like this. So during evaluation, we do not care about gradients. We won't calculate them to update our model. We do not need it. So to avoid spending extra time and compute resources to calculate these gradients, we say PyTorch do this without gradients. We do this torch.noGrad, no gradients, do this operation. Probably can even do it like this. Okay. Another way to do the same thing is to do like this, but it's for those who understand what it means. It's called decorate in Python. You can Google it. Usually you would do with torch no grad. I will update the notebook to include it. And finally, when you do training, you just train for one epoch, you evaluate your models, and you train for the second epoch, you again evaluate your model, etc. And you do this for several epochs. So I didn't mention what is epoch. So before I said that we train for num iterations, for the total number of iterations, but n num iterations is length of your data loader multiply by n epochs. So basically this means let's go over our data loader n epochs times. And this would result in this many iterations. So there are like two paradigms. You can look at your training iteration-wise or epoch-wise, like step-wise or epoch-wise. Yeah, and one last thing, because we are training deep neural networks, we probably need huge computational power. and we cannot do it on our own laptop without like on a CPU. We need special hardware, which is called GPU, like graphical processing unit, which increases the speed and calculations. And if we are having an NVIDIA card, it's called CUDA, and we can say PyTorch, put everything on CUDA to ensure that you are running everything on GPU and not on CPU. So in code, this also means that before doing any calculations, we need to do this line, which says, put this image on this device, which is our GPU. Put this label on this device, which is our GPU. And let's say we have 10 epochs. Finally, how we run it, we create our fully connected network. We say that we have 10 labels. We should put our network on device 2 on GPU. We create optimizer to say like whether we want to use HGD or Adam or AdamW to optimize our model. And in the first argument, we pass parameters of our model. So which weights to train, to modify with this optimizer. And some arguments like learning rate, let's say 3e minus 4 because of this Twitter meme I talked about yesterday. So what about TPU runtime? So TPU is not working with PyTorch. It's for TensorFlow and JAX. Yeah, and we define scheduler like cosine annealing, which will decrease learning rate like this. Also, we need to pass optimizer for the scheduler. And here, the only thing we need to describe is what is the minimum learning rate and what is the total number of steps. So number of epochs multiplied by the length of our data loader. And if we run it, we'll see that, okay, one epoch is running. This is our progress bar. And we are plotting our results. And we see that our loss goes down. In blue, we see training loss. In red, we see validation loss. And here we see accuracy on our validation. We see that we start with some not so well accuracy, but as we train our model, the quality of our predictions becomes better and better. Yeah, and the loss goes down and down. And we could do the same thing for the convolutional network, exactly the same stuff, just ConvNet here instead of FCNet. And it would result in this kind of plot, or with ResNet with this kind of plot. And notice that convolution and ResNet achieved much better quality than fully connected layer. Yeah, so here the maximum accuracy is 96.7, and with convolution is 98.71. And that also again shows that convolutions are better than fully connected layers when you work with images. Yeah, so this stuff we'll cover it on Friday, not worry. Yeah, so that's all for today. I'm very sorry that it took 35 more minutes. Hopefully you hope that you're alive, more or less. No, not alive. Could you please repeat how does ResNet code works again? So you define your convolutions here, which is how to go from here to here, these two layers. Then let's avoid this for now. You just say, okay, output is self.convx, and you add residual connection by not modifying x. You just say output plus, your final output is output plus x. We had this downsample convolutional here, which will be located here because sometimes your input channels and your hidden channels may be different. Question back from the lecture. Is ResBlock just a method of not getting vanishing grains by adding an argument from a few previous layers, or I've lost it? So ResBlock uses this residual connection and it reduces this residual connection to improve gradient flow. Yeah. So this residual connection allows you to improve the gradient flow and also let you avoid this degradation problem when you have large neural networks, deep neural networks. Good. Good. Yeah, I guess that's all for today.